This video is on soil mechanics, focusing on soil formation, classification, and basic definitions as part of Geotechnical Engineering 1. Geotechnical engineering, or soil mechanics, is the branch of civil engineering that treats soil as an engineering material. It is vital for foundation design, earth dams, stability of slopes, and more. According to IS 2809-1972, soil is the unconsolidated accumulation of solid particles from the physical and chemical disintegration of rock. Geotechnical engineering has a wide scope, including the design of foundations for buildings, tunnels, highways, bridges, and other large structures, where the interaction between the structure and the soil is critical. Soil formation, or pedogenesis, begins with weathering, the breakdown of rocks into soil. Physical weathering, through processes like exfoliation and freeze-thaw cycles, breaks rocks into smaller pieces. Chemical weathering, involving reactions like carbonation and oxidation reduction, further changes the rock composition, often involving water. Physical weathering agents include wind, water, temperature, and ice. Residual soil forms in place from the bedrock, while transported soil is moved by agents like wind or water. The mode of transport influences the soil type, such as air/wind creating dunes or aeolian soil. Soils are generally classified as gravel, sand, silt, or clay based on particle size. Soil classification systems include particle size, textural, Highway Research Board (HRB), Unified Soil Classification System (USCS), and Indian Standard Classification System (ISCS). Consistency and various soil parameters are also used for classification. The Highway Research Board, or HSB classification, categorizes soils and soil aggregate mixtures using sieves and characteristics like liquid limit and plasticity index, assigning a group index to aid in subgrade evaluation. The Unified Soil Classification System, or USCS, classifies soil based on grain size and plasticity characteristics. The system uses symbols and brief descriptions for major divisions like gravels, sands, silts, and clays, along with laboratory test results for finer detail. Sand is a coarse-grained soil primarily composed of quartz and feldspar. It is defined by having more than 50% of the material larger than 75 microns, with most of the coarse fractions smaller than 4.75 millimeters. Sand is subdivided into coarse, medium, and fine based on grain size. Clay is a fine-grained soil with particle sizes smaller than 0.002 millimeters, denoted by C. Unlike sand, clay is classified based on its plasticity, specifically using the liquid limit. On the plasticity chart, soils plotting above the A-line are classified as clay. Silt is a fine-grained soil where over 50% of particles pass the 75-micron sieve, and the soil plots below the A-line on the plasticity chart. It is categorized as ML, MI, or MH based on its liquid limit and compressibility, with organic silts classified as OL or OH. Soil is a complex engineering material with a microstructure of particles and spaces that can be filled with air or water. Unlike most other engineering materials, soil exists naturally as a three-phase system: solid, liquid, and gas. 4 fundamental weight-volume relationships define soil properties. Void ratio E is the ratio of the volume of voids to the volume of solids. Porosity N is the volume of voids to the total volume. The degree of saturation S is the volume of water to the volume of voids. Water content W is the weight of water to the weight of solids. Various equations connect the weight and volume relationships within soil mechanics. These formulas are crucial for calculating parameters like moist unit weight, dry unit weight, and the relationship between void ratio and the degree of saturation, where SE equals WG_S. Additional weight-volume relationships involve density, dry density, and saturated density. These equations utilize specific gravity, G_S, and the unit weight of water, gamma_W, to define the soil's state in different moisture conditions. This table summarizes the various forms of relationships for moist unit weight, dry unit weight, and saturated unit weight, providing comprehensive formulas based on different known parameters, such as water content, void ratio, and degree of saturation. Here is a solved example problem to determine the specific gravity of soil solids and the field void ratio, given the saturated unit weight and water content. Assuming a unit total volume, the solution involves calculating the weight of solids and water and then using the volume relationships to find the void ratio and specific gravity. Relative density, or density index, is a measure of the compactness of a soil deposit. It is defined as the ratio of the difference between the void ratio in the loosest state and the natural void ratio to the difference between the loosest and densest states. Relative density helps describe the soil deposit, ranging from very loose to very dense. Atterberg developed a method to describe the consistency of fine-grained soils. Depending on moisture content, soil behavior changes, dividing into 4 basic states: solid, semi-solid, plastic, and liquid. These states define the plasticity and structure of the soil.